Hello, this is instructor Rick Powers for Western Technical College, Basic Statistics. Lesson number 22, Sampling Distribution of the Sample Mean. In doing statistics, most of the time we are using information from samples. So a big part of statistics is the process of getting information from a sample, which will apply to the population of interest. For example, if I want to know something about how a certain chemical affects people with asthma, I don't have access to everyone in the population to measure those effects. So there needs to be a way to interpret results from a smaller group to apply that to a larger group. To me, it's pretty amazing how we can use mathematical tools to actually make that process work. However, we should also bear in mind that mathematical assumptions are required, and the methods of measuring and sampling are not perfect either. Hopefully, you're aware that statistics deals with numbers that change. This is called variation or variability. One source of variation is the fact that samples are only parts of the population. Every sample could be different. This is called sampling variation. The amazing part is that we can predict the distribution of certain measurements as long as certain assumptions are made. We even have some control over the variation in our samples. Also, it turns out we can use the normal distribution in a lot of cases or make a few adjustments to it. Here's how it works. Let's start with a bell-shaped set of population data. I'm using X for each data point. We'll say the mean is 120 and the standard deviation is 16. Next, we decide to take a lot of samples at random. Each sample will have 64 observations, so we say that n is equal to 64. And for each sample, we take the mean. What is the distribution of the sample means? In other words, what will those measurements look like on a graph? The sample numbers will not all be the same, but hopefully it makes sense that most of them will be close to the population mean. I'm using X bar as the symbol for the sample mean. Note, number one, the distribution has a center at the same value as the population mean. Number two, it's more narrow than the data itself. And number three, it is also bell-shaped. Now comes part of the magic. There is a formula for the standard deviation of the sample means. So we can predict how accurate our samples will be. Here's that formula. Sigma sub X bar, or the standard deviation of the sample means, is equal to sigma, or the population standard deviation, divided by the square root of n being the sample size. With this in mind, we can have control over the sampling variation of our data. If the sample is large, then the sampling variation will decrease, and the sample means will be close to the population mean. But this was based on having bell-shaped population data. What if it's not? Let's look at a different set of data, the miles that someone travels to get to school. Here the mean is 5 and the standard deviation is 4. This is very skewed since a lot of people live close, but there are people who travel 10, 15, 20 miles or more. But if the sample size is large enough, then we can apply something called the central limit theorem. It tells us that we will get close to a bell-shaped distribution of sample means if our sample size is large enough, if n is greater than 30. In our example, the center of the sample means will still be equal to the population mean of 5. And with a sample size of 64 and population standard deviation of 4, our standard deviation for the sample means is standard deviation equal to 4 divided by the square root of 64, which is 4 divided by 8, which is 0.5. So you see a 5, which is the center of the sample means, and then they are pretty close to that. Now we have the tools that we can use. If we know the population mean, the population standard deviation, and the sample size, then we can find the mean and adjust the standard deviation for the distribution of the sample means. And we can use all the technology of the normal distribution to find what to expect from our samples. End of lesson 22.